What happens inside your computer when you move your mouse while a file is being copied, or how does a network card download data without freezing your entire system? I am Pritham Kumar, and for my COA project, I built a real-time interrupt handling and DMA data transfer emulator to answer exactly that. Today, I'm going to show you how a CPU manages emergencies using the ISR pipeline and how DMA controls steal cycles to keep your PC fast. So this is what I built, so-called CPU interrupt and DMA emulator. This emulator features a complete of 8 vector interrupt descriptive table IDT. Each IRQ from the keyboard to page faults has a specific priority and handler address. On the left, you can see the program counter and stack pointer. These aren't just numbers, they actually track context saving. Notice the interrupt flag. When an ISR starts, this flips to off. This prevents a secondary interrupt from causing a stack overflow unless it's a non-maskable interrupt (NMI), which I have mapped to the escape key. Let's fire a keyboard IRQ. Look at the context stack. The CPU immediately pushes the current PC and registers onto the stack. This is context saving. Once the ISR, the interrupt service routine, finishes, the CPU performs an EOI, end of interrupt, and pops the stack. The CPU resumes the main task exactly where it left off. So no data loss, no lag. Now let's talk about the direct memory access DMA. Usually the CPU has to move every byte of data. That's a waste of high performance brain. My emulator demonstrates the three industry standard DMA modes. First is single mode. The DMA steals one clock cycle per byte. As you can see on the timeline, the CPU stays green, active, while the DMA is blue. CPU utilization remains at 98%. Now comes the burst mode. They take turns, 8 bytes for DMA, 4 cycles for CPU. It's a balance of throughput and responsiveness. Now comes the block mode. This is the bulldozer. The DMA grabs the system bus and doesn't let go until the transfer is done. What's the CPU status? It turns gray and stalls. The transfer is fast, but the system is frozen. Now we'll go with the comparison of three modes. After running the comparison, the bar chart gives us the verdict. A block mode is the most efficient for the hardware, but the worst for the user experience. Single mode is the ninja that keeps the OS feeling smooth. I built this using HTML5, CSS3, and vanilla JavaScript to ensure the timing of cycles is accurate to the microsecond. So in conclusion, this project helped me truly understand the handshake between hardware and software. If you are a computer science student, I highly recommend building an emulator like this. It makes an abstract COA concepts feel real. Thanks for watching. I have linked the project details below. I am Pritham and I'll see you in the next one. Bye.